So Norbert Fried of Satisfy Israel Limited is the verification manager with a demonstrated history and proven record of successfully leading SOC verification of several hardware design takedowns. Skilled in semiconductors, debugging, functional verification, and UVM, is a strong professional with a Master of Science MSc in Electrical Engineering from Tel Aviv University. Over to you, Norbert.
Okay. Hi, thanks, Mike. I will present 3 SOC challenges that we faced in our last project that we developed. I presume that at least 2 of them will be quite generic that probably many of you are facing. Just one word about Satisfy before I start. We're a startup company doing products in satellite communication industry. The 3 challenges that I want to present is how we do verification using Matlab reference models in UVM environments. The second challenge will be how we can, on the fly, generate stimulus on the same design interface from different sources, like a VIP or the design itself. And the third one is in case you have to do gate level simulation and you can't avoid them, what you can do to make it a bit easier. The first one is basically what we want to achieve if you need to run simulation using Matlab as a reference model. You would do a few things. The first one, maybe one of the most important, is to have a flow that you can run the simulation without using Matlab license. Matlab license is very expensive, and if you need to run a big regression with many simulations in parallel, this can be very painful. So there is a built-in tool, not a built-in tool, but there's a tool that comes with Matlab that you can compile the Matlab code to the C. And basically, after that, using DPIC, you can connect the simulation with Matlab. There are some significant challenges doing that, as the memory structure on this C code that comes from Matlab is something that is not plug and play to connect using a DPI interface. The point that I want to focus is not on that problem, but just to give an overview of the high-level flow that you would like to achieve. There are many challenges to achieve it. So starting with basically simulation flow would be that you start, you would like the Matlab, you would try to run on the fly a Matlab simulation, creating several inputs. One is the generated input data, samples, or whatever you do that you want to drive into the design. The second thing, you would like to generate the configuration of the design based on the input vector that you want to drive in. So you want to be in a position that both the design and the Matlab are doing exactly the same simulation. And the third point, you will need from the Matlab to give you the test points on all those points that you want to monitor, and at the end compare the DUT versus the reference from the Matlab. One important point to mention is that preferably you will have a bit exact Matlab model. So then the comparison between the buses in the RTL will easily match with the buses with the vectors from the Matlab. So in this diagram that I'm sharing, basically, it starts from the left to right, and it starts creating the UV environment should be the one that during the build phase or the run phase, you start and create a Matlab call to generate all the test points, input vectors, and the expected results, basically in 0 time. And then when you start the simulation, you start driving the data at the right interfaces in the design, and the test points, again, are monitoring the right buses from the DUT. Obviously, using a good configuration environment, you can easily turn off monitors. You can change the point that you grab the data. So a test point that in some simulation is used to be a monitor, next time it can be used as a driver. So having a good and robust environment, you can easily navigate and use the different inputs from the Matlab, different outputs from the Matlab for different reasons. The next challenge is how we create an environment in which you want to support runtime switch between a VIP and real design during the simulation. We don't want to create obviously we don't want to create changes in the RTL code in order to replace design pieces with the VIPs. We also don't really want to use if-defs, so we not have to create multiple simulation snapshots. And there is obviously a problem when you drive from multiple places in the same buses that you have contentions. So I've shown here like a kind of a generic diagram of on the left side, the green one is the DUT. So you can have several masters connected to different, maybe to a fabric, you have different slaves. You have a lot of sideband signals connected to these masters like clocks, resets, handshakes with maybe processor interrupts, whatever you have in the design. Then you have an interface that you connect to one of the masters in the design, and you have a VIP that is capable to drive that interface. It can be a third-party VIP, it can be something you develop, doesn't matter what is the interface. But at the given simulation, you can either need to drive this bus either from the real design in the chip, the M2 master in this diagram, or from the VIP. And in some cases, you even want to be able to switch between them. So I can start a simulation in which I may want to quickly initialize the DUT from the VIP, and then on the fly switch off the VIP and let the design to drive the interface. The third problem is what can be done in order to shorten the gate level simulation bring up and debug. I would split it in two phases. The one that you can do before you have a gate level during the RTL stage. And the second one is after you have the gate level. So before you have when you are still in the RTL phase, there are some steps that can be done which are not listed here, that in some cases you can completely avoid gate level simulations. But in case that you can't do those steps, or still there is not enough confidence that gate level simulation can be avoided, you can do at least some of the following. So maybe one of the basic and the better value that you get from it is to run a regression using X propagation enabled. Most of the simulators today are supporting under license X propagation. There are other things that can be done avoiding X propagation licenses, but this would be the easiest. The second one, you need to prepare the environment so you can easily replace big blocks with empty or black boxes. So when you try to compile gate level, you will be able to replace those with empty boxes, so the compilation and operation of the gate level will be significantly faster. You can start to create a list of all the deposits on all those places that are in uninitialized registers or some memories that can cause failures in the gate level due to more pessimism approach versus the RTL. And maybe one of the most important will be to create a light environment in which you can pass at least reset simulation, which will be the first one that you want to start to migrate to the gate level DUT significantly faster and easier from both perspective of how much time it takes to compile and elaborate, and the debug of the environment just to see that you can at least get off the reset. So these are like some basic steps that can be done during RTL phase. Now that you already have a gate level netlist from the physical design team, you would like to start without SDF in the first place. SDF is annotating the timing value from the physical view of the design. It's a standard delay format. So you would like to start without it. Obviously, you want to start with a light environment. And even in the light environment, if you are using some VIPs connected to some of the interfaces in the design, you would need to start to port those that are the must be running, it must be enabled to pass the first simulation, and the porting is basically to remap the interface to the new hierarchy in the gate level, which might be different. And obviously, you would like to disable the timing check on the first flop in the synchronizer cell, as it will these flops have a big, large probability to violate and to create excess that will fail your simulation. This is all I had.
Thank you very much.